Let's discuss multiplying decimals. So the copies of language is very helpful with multiplying whole numbers, multiplying fractions, and multiplying decimals. So let's use the copies of language on this problem. Let's draw a picture and then let's try it with decimals. So 3 times 4. That would be 3 copies of 4, and we could draw a picture and then find our product, which would be 12. For 3 times 4/10, we would write our copies of language as 3 copies of 4/10. So each one of those grids is there. You can think about how you would shade those and draw those pictures. Take a minute and see how you would do it. All right, is this how you did it? So again, with the whole numbers, 3 copies of 4, so I put 4 in one group, and then I copy that group 3 times for a total of 12. For the second one, 3 copies of 4/10, we use orange strips to denote tenths, so we highlighted 4 of the strips in each one of the grids, so we have 3 copies of 4/10, and then you can imagine us rearranging those into full grids, and we would have 1 full grid and then 2 strips left over. So that would be 1 and 2/10. You might relate how that multiplication product changed. When we were multiplying a whole number times a whole number, we got a whole number. When we were multiplying a whole number times tenths, our answer ended in the tenths. Our place value was shifted over 1 to the left. This relates to our powers of 10. Look at the patterns of multiplication by powers of 10. What's happening to the place value? Try these 6 problems and see if you can think about and state what's happening to the place value. So the place value is shifting to the right the number of zeros that are in the factor of 10 in the problem. So with 3 times 10, there was 1 0, and it shifted to the right 1 to go from 3 to 30. You can use the same idea in estimating and using powers of 10 to multiply decimals. So if we were trying to multiply 1 and 4/10 times 3, first I want you to think about that. 1 and 4/10 times 3. That would be about 1.5 copies of 3. So 1 copy of 3 would be 3. A half a copy of 3 would be 1.5. So if we add those two together, 3 plus 1.5, our answer should be around 4.5. You can use that same thinking and your powers of 10 to multiply decimals. Try it on these problems and then look at the next slide. Really think about how you estimate. So I know that 14 times 3 is 42. So I use that information to know that all of my answers that have a 1 and a 4 in one of the factors and a 3 in the second factor will have those digits 4 and 2. The only thing that's going to change is the place value. So I have some explanations there. Tenth times tenths is hundredths. Hundredths times tenths is thousandths. And then you can follow a similar pattern when you're doing 3 times 8, because we know that 3 times 8 is 24. The only thing that's going to change is where my decimal point goes. And then 4 times 21 would be 84. And again, what moves is my place value. Let's investigate this further. So multiplying decimals. Why does the algorithm for multiplying decimals work? So this is probably your standard algorithm for multiplying decimals. Ignore the decimals, multiply as if they were whole numbers, then place the decimal in the product so there's the same places to the right as the sum of the places in the factors. Why does that work? Let's take a look at an example. So on this problem, I want you to convert the decimal to a fraction, multiply straight across, and then put it back in a decimal. So 2/10 times 4/10, we read those decimals and the fractions the same way. So if we multiply straight across, we get 8 over 100, or we could read that fraction as 8 hundredths. So 2/10 times 4/10 must be 8 hundredths. Notice that there's one decimal place to the right of the decimal in each one of the factors for a total of 2. And in our product, there are 2 decimal places to the right of the decimal in our solution. So, what pattern did you notice? So here's the breakdown of it. The algorithm is a shortcut for finding fractional values for each product. Because the process works without exception on all decimals, it's used because it's quicker and takes little effort. Unfortunately, if you show that to students first, students have no idea why they're counting places to the right and putting the decimal point in the corresponding spot in their solution. They just hope that whoever told them it works, which was you as the teacher, was right and their answers are correct. The only way for a student to verify the answer is to estimate to see if their estimation places the decimal in the same location. So make sure you make sense of why we need to understand how the algorithm works. Now let's move to dividing decimals. So again, we're going to start with pictures and our copies of statements. So rewrite the division statements using copies of and word names. Then represent the decimal problems using the grids. So 12 divided by 3 is really asking how many copies of 3 are in 12. And the second question, how many copies of 3/10 are in 1 and 2/10? Let's take a look at it. So if I have 12 things and I want to know how many copies of 3 are in 12, I'm going to circle groups of 3. I end up getting 4 groups of 3. So there's 4 copies of 3 in 12. If I do it with the decimals in the grid, I want to know how many copies of 3/10. Well, 3/10 would be 3 of these columns. So that would be 1 copy, 2 copies, 3 copies, and then this last one would be our 4th copy. So did you notice that 1 and 2/10 divided by 3/10 is still the whole number 4? Pay attention to that. Both of those problems have the same answer. Why is that? Dividing decimals. Why does the algorithm for dividing decimals by decimals work? So your traditional algorithm was probably move the decimal in the dividend and the divisor the same number of places, then divide. And you did this to get rid of the decimal point in the divisor. So how we're going to investigate this further is we're going to write each division problem as a fraction. Then we're going to multiply the numerator and denominator by a unique one that omits the decimal from the divisor. And then we're going to simplify. So 2 and 4/10 divided by 6/10, if we write that as a fraction, usually we don't have decimals in our fractions. So we're going to get rid of those by multiplying by 1, but in this case that 1 is going to be 10 over 10. Notice that eliminates our decimal in our numerator and our denominator. So we end up with 24 divided by 6, which is 4. So our answer to 2 and 4/10 divided by 6/10 is the whole number 4. So think about this. We changed division problems with decimal divisors into equivalent division problems without decimal divisors because it's difficult to understand the meaning of the decimal divisors. The meaning of 3 and 5/10 divided by 5/10 is how many copies of 5/10 are in 3 and 5/10. When we change the problem proportionately by moving the decimal in both the dividend and divisor, it's easier for us to understand and use the traditional algorithm. Think of powers of 10 with division. What happens when we divide by powers of 10? Try these 3 problems and then describe what's happening to the place value. Did you notice the place value is shifting to the left, the number of zeros that are in the divisor? Notice that's the inverse operation of what happened in multiplication. In multiplication, we were going to the right. In division, we're going to the left. So you can try these estimation problems with powers of 10. So you know what 24 divided by 8 is. You can estimate the other 2 divisions. Same with 42 divided by 7. See if you can estimate those. Here's the answers. It might help you to think of it as multiplication. So you place the decimal point in the right place. So what patterns did you notice? If students understand the patterns and what's happening in dividing and multiplying decimals, the algorithm is not needed. It usually develops naturally, but it's not necessary. And it doesn't necessarily develop. As long as the students are understanding the mathematics and able to compute it, they're doing fine. Hope this helped you with multiplying and dividing decimals.